Today's class we're looking at the mock test we wrote yesterday. It's based on chapter 17 from Brown's book. This question number 1 is number 17.14, chapter 17, question number 14. And it involves a buffer where we're told that the KB is 1.7 times 10 to the minus 9. What I did in this question is I recognized that pyridine hydrochloride acts like pyridinium chloride behaves like a weak acid, giving pyridine as the conjugate base. So I solved for the value of Ka, which was 5.88 times 10 to the minus 6, and I set up an ice table. I asked in the question to solve it two different ways. So I plugged in the values of the concentrations initially, and we start off with a concentration of H plus of 0, and we assume that a certain amount X of the pyridinium chloride, dissolves, so that we get 0.35 minus X at the equilibrium. That same amount X dissociating produces an increasing amount of pyridine by plus X, so that you get 0.21 plus X, and then at equilibrium you have H plus concentration of X. So you set up your equilibrium equation like I did here, products over reactants, cross multiply to get the trinomial, which is set to 0. And when we solve for H plus, I did it with my calculator. My calculator has a function where you plug in the 3 numbers from the trinomial, and it gives you the 2 values for X. We discard the negative value, and we get that the H plus concentration at equilibrium is 9.8 times 10 to the minus 6. We plug that into the pH equation, we get a pH of 5.01. You can also, alternatively, solve the equation using the Henderson-Hasselbalch equation. All you need to know is the pKa of pyridine, pyridinium chloride, and it turns out to be a negative log of 5.88 times 10 to the minus 6, you get 5.23, and then we plug in the concentrations, A minus representing the pyridine, and this is the pyridinium chloride, it's the protonated version. And again, you get a pH of 5.01. Each red arrow is what I was looking for in your test paper. So you can see that getting the correct answer gains you 2 marks. What I want to see is the whole process that went into solving the problem. You can get a lot of part marks if you get at least even halfway. In the next problem, which is from number 28 of chapter 17, you're asked to solve for the pH of a solution that is composed of 6.5 grams of sodium dihydrogen phosphate and 8 grams of sodium hydrogen phosphate, the disodium monohydrogen phosphate. So I set it up as though it was a weak acid. It is basically the second dissociation of phosphoric acid. You see that phosphoric acid dissociates once to give you a proton with the Ka sub 1. Then the second dissociation, the hydrogen phosphate, gives you hydrogen phosphate, Ka sub 2. And the third dissociation, the hydrogen phosphate, gives you the phosphate anion, that's Ka sub 3. So we're looking at this equation here. That's what's happening. And the K value they report for that is 6.2 times 10 to the minus 8. Which seems to indicate that it's actually a slightly basic substance. But I solved it as though it was a weak acid. No harm comes from that because in the Henderson-Hasselbalch equation, which I used to solve it, I recognized that the A minus was this one, and the HA was this substance. The one that has 1 proton more than the other one is the acid, and the conjugate base is on the numerator. So as long as I set it up correctly over here, I'll still get the correct answer. So here I'm finding the number of moles of dihydrogen phosphate, the grams divided the molar mass. Here's the molar mass calculated. That's the number of moles. We were told the solution has a total volume of 3.355, so that gives us a concentration of the dihydrogen phosphate over here. We did the same thing for the monohydrogen phosphate, and we obtained this concentration. We found found the Ka here. The pKa is 7.21. So we plug all these numbers into the Henderson-Hasselbalch equation, and we get that the pH is 7.22. This question had 19 steps in it. That's how many marks I attributed to it. Third question comes from 1739, chapter 17, another question number 39 from Brown. And it asks us to do a titration. And I started off the titration by, the calculation by saying, okay, we're titrating 20 milliliters of hydrobromic acid at a 0.2 molar concentration with 0.2 molar sodium hydroxide. So the concentration of the titrant and the substance being titrated is the same, which makes the problem kind of simple. But I started the calculation in the way I would have done it if I'd had concentrations that were different between the titrant and the substance being titrated. So I would have found out how many moles of NaOH I had. That's what's titrating. That's what we're having the burette that's dropping into the substance, and this is what's being titrated. And it turns out we have 4.0 times 10 to the minus 3 moles of HBr and 3.0 times 10 to the minus 3 moles of NaOH. So there's an excess of hydrobromic acid, which means there's an excess of H+. So that's what we have to find out, the concentration of H+, to find out the pH. And we do that by finding out the total volume. Remember, during a titration, as you're adding titrant, you're increasing the volume of the solution. So we have 15 mLs added to 20 mLs at the end. That's why we get a 35 mL total volume at the end. And that gives us some H+ concentration of 2.85 times 10 to the minus 2. It gives us a pH of 1.54. So the titration is not at completion yet, so it would be acidic. In part B, I decided let's simplify this because we know that the concentrations of both titrant and the substance being titrated is 0.2. So all we really need to find out is what's in excess. When we reach close to the equivalence point, we've added 19.9 mLs of sodium hydroxide. So we're very close to equivalence, but we still have a slight excess of H+. So all we really need to find out is what is the concentration of the hydrogen ion. We're 0.1 mL away from equivalence. So what we're finding out here is how much H+, HBr is in excess. So that's why I used 0.1 here. 20 would give us equivalence, but we have 19.9. So 0.1 divided by 1,000 gives us that volume in liters, times the concentration of HBr. I should write that here just so that you'll understand what I'm talking about. And then this is the total volume of the solution. So that gives us moles divided by liters, gives us the H+ concentration, 5.12 times 10 to the minus 4 molar of H+. That would give us a pH of 3.29. Box around it just to make it clear. At equivalence, the pH is 7. I didn't do a calculation because whenever you have a strong acid being titrated with a strong base, the pH is going to be equal to 7 at equivalence because the conjugate acids and bases of strong acids and bases do not affect pH. D, we're a little bit past the equivalence point. We've added 20.1 mL. So now the question is to find out the excess of hydroxide. Same calculation, 0.1 over 1,000 times 0.2 divided the total volume, which is now 40.1 instead of 39.9. And the OH concentration comes up to 4.98 times 10 to the minus 4, which gives you a POH. Be careful with that. It gives you a POH of 3.3. So if you want to find the pH, you subtract that number from 14, you get a pH of 14.7. In the last one, which is being blocked by this apparatus, let me just take that off for a second. In the last one, we have an excess of sodium hydroxide added. So we're going to find out what the concentration of hydroxide is again. And we have 15 mLs times the 0.2 molar concentration. Here's the total volume. This 15 represents the excess of base because to reach equivalence you only need 20. So an extra 15 was added by adding 35. 35 minus 20 gives you 15. That's where I got this number. And that's the concentration of the sodium hydroxide. Just write that down just so you can see what I'm talking about. And here's the final volume, final total volume. Therefore, the OH minus concentration is 5.45 times 10 to the minus 2. And you get a POH of 1.26, which translates to a pH of 12.74. The fourth question in the test comes from chapter 17 of our textbook, Brown, and it's number 73. The question asks to calculate the pH of a solution that contains 35 grams of furoic acid and 30 grams of sodium furoate in 0.25 liters of solution. So the part of the difficulty in this question, which surprised me, was to find out what the formula of furoic acid was. Well, remember that a conjugate base, sodium furoate, is given to you. So to find the acid structure, simply remove the sodium and add an extra hydrogen, because the difference between the acid and its conjugate base is that one proton has come off. And that's what I wrote here. Here's the furoic acid, here's the furoate, and there's that proton that came out. So we find the molar mass of the furoic acid, the number of grams. Here's the molar mass. That gives us the number of moles. We divide by the volume of the solution, and it gives us the concentration of furoic acid. We do the same thing on the other side for furoate. Remember to include the mass of the sodium, because the solution is prepared by mixing a powder, so the sodium would be present when you're mixing the powder. So there's 134 grams per mole of furoate, sodium furoate, and there's the molar mass, the concentration of furoate. We plug all these values into the Henderson-Hasselbalch equation. We found the pKa of furoic acid to be 3.17 by taking the negative log of the Ka value that was given in the question, and we get a pH of 3.02. So it's an acidic solution.